Balancing equations was the main concept of Chapter 7. Now we're going to start to move into the material of Chapter 8, where we're going to look at the types of reactions that can occur, the types of balanced equations basically that we can end up with. Our goal here is to look at the major types of reactions so that we can identify the type of reaction anytime we see a reaction listed. We want to be able to do net ionic equations for precipitation reactions and acid-base reactions. And the most important final step is we want to get to the point where we can look at the reactants that we have and understand what's going to be produced, what are the products going to be, and write the full balanced equation. To get to that point, we've got to have a really good understanding of the types of reactions that occur. To understand the types of reactions, our starting point is what is causing reactions to take place. These are known as the driving forces of reactions. A driving force is a change that causes the reaction to go from reactants to products. It just doesn't happen out of nowhere. It has to happen for a list of possible reasons. The first of these reasons is the formation of a solid. This is going to be a specific type of reaction that we always see. The most common example of this is a precipitation reaction, which is going to be the focus of the beginning of this chapter. We have the formation of water. Our most common case of this is what's known as an acid-base reaction. The transfer of electrons is the third thing that can be a driving force. This is going to be all of our oxidation reduction reactions. And we also occasionally see the formation of a gas, which can fall into many of these other categories. So based on the type of driving force that is taking place, we have a pretty good idea of the type of reaction that we are dealing with. The first type of reaction that we really want to focus on is precipitation reactions. And these precipitation reactions are going to be the focus at the beginning of this chapter. We will then move into the next video looking at how to write net ionic equations for precipitation reactions. Once we get that mastered, we'll move on to acid-base and then into our oxidation reduction reactions. A precipitation reaction is a reaction in which a solid product is formed. So we generally are taking two aqueous compounds, mixing them together, and then a solid is produced in the reaction. That solid is known as the precipitate. So that solid that forms, usually forms a cloudy solution, is known as the precipitate. Most precipitation reactions and most acid-base reactions are another type of reaction known as a double replacement. So it actually falls under both categories. You can have a double replacement reaction that's not precipitation, but pretty much the majority of our precipitation reactions will also be double replacement. In a double replacement reaction, the metal cations and the nonmetal anions are going to switch partners. So the positive of one compound is going to bond together with the negative of the other compound. It's always positive bonding with negative, and sometimes you see this called as double displacement. An example of this might be something like AgNO3, silver nitrate, aqueous, reacting with potassium chloride, aqueous. When this reaction takes place, we basically have the partners, Ag and K, switching with the negative ions that they're paired with. So Ag bonds with Cl, Ag is plus 1, Cl is minus 1, so we get AgCl. And K bonds together with NO3. Now to really understand what's going on in the products here, we need to be able to understand, is this a solid that's being formed or is this an aqueous compound that's being formed? And the only way to know this is something called solubility rules. And to understand what's really going on when we have an aqueous solution of an ionic compound. What we're going to find later in this video is that we're going to learn that this would be a solid and this would be aqueous. To understand that, we're going to have to learn something called the solubility rules. But before we move on to the solubility rules, let's talk a little bit more detail of what's really going on when something goes into solution. What happens when something dissolves or doesn't dissolve in solution? An ionic compound, when it is put into water, will dissociate. Dissociate means that the two ions, the positive cation, negative anion, separate from one another. So instead of being held together by that attraction of the positive and negative charge, they're going to separate. The water molecules will surround each ion, and the ions will no longer be bonded together, but they will be separate within the solution. If you evaporate all the water, then they will come back together. We refer to a compound that dissociates in water as a strong electrolyte. You may have seen this a number of places. The one that should probably pop right into your head is Gatorade. Gatorade always talks about replacing your electrolytes. If you actually have a bottle of Gatorade, go look at it for a second. What you will see is it lists you have potassium and sodium in Gatorade. Potassium and sodium ions. Those are individual ions dissolved in the water that makes up the Gatorade, and these are your electrolytes. Your body needs both potassium and sodium for a number of cellular processes to function correctly. You have a potassium pump, a sodium pump, and a number of cells. To understand when something dissolves or when something doesn't dissolve, we need to look at the solubility rules. These are found in your book in Table 8.1. These are the common solubility rules. The first three of these solubility rules are the only three that you need to know by memory. So this group here. The rest of the solubility rules will be given to you. If you actually remember in class those blue periodic tables that we work with, if you flip them over, on the back side of that blue periodic table is a list of the remaining solubility rules. The three solubility rules that you have to have memorized are nitrates. Anything that's bonded to nitrate will always dissolve in water, will be soluble. Second, potassium, sodium, and ammonium. Those three cations are always soluble. Anything bonded to those three cations will be soluble. And third, chloride salts, and generally you can think of this as any halogen, iodine, bromine, fluorine, will be soluble unless they are bonded to silver, lead 2+, or mercury 1+. So these are the three major exceptions. Generally always going to be soluble except with silver, lead 2+, and mercury 1+. And you remember silver is always 1+. That's its charge that we know from the periodic table. So if you think back to that earlier reaction we were looking at, we had AgCl. Chlorine is soluble, dissolves in water with everything except silver 1+, lead, or mercury. Well, in this case, we have silver 1+, so that's why this is a solid. Nitrate salts and potassium salts both are always aqueous, so that's why this is aqueous. If you even look at our original starting things, silver nitrate has nitrate in it, so it is always aqueous. Potassium is always aqueous. Chlorine is aqueous with everything except lead, silver, and mercury. So in this case, both ions would tell you that is definitely aqueous. So these are the three solubility rules you need to know. And we actually look at this reaction to see what's really going on in solution. When you put silver chloride, or silver nitrate, and potassium chloride into solution, it's going to form those individual ions. They're going to dissociate into those individual ions. When the silver and silver and chlorine come close together, they will form a solid because silver chloride is not soluble. Potassium nitrate still is, so it remains separated in the solution. You need to learn those three solubility rules so that we can start to look at precipitation reactions and start to do the balanced equation, what's known as the complete ionic, and net ionic to really show everything that's going on in a precipitation reaction, and that'll be tomorrow night's video.